Hey gang, let's go over. First of all, welcome back to 4600. Let's go through the three homework problems I suggested or recommended at the end of 5.1 part 1. So exercise 5.1, or no, excuse me, strike what I said a minute ago at the end of section 5.2 part 1. I don't think I said it that way. But anyway, let's look at the first exercise that I asked you to do. So it says contracts for two construction jobs are randomly assigned to one or more of three firms, A, B, and C. All right. So that means we can randomly assign any of these two construction jobs to just one or a combination of two of these particular places. So let Y sub 1 denote the number of contracts assigned to the firm A, and Y sub 2, the random variable Y sub 2 represent the number of contracts assigned to firm B. Recall that each firm can receive 0, 1, or 2 contracts. So it's kind of telling us right off the bat what our range is for both the possible values for random variable Y sub 1 and random variable Y sub 2. Okay. And it says find the joint probability function for Y sub 1 and Y sub 2. This is going to be very similar to one we did in homework, or we did in the lecture last time. So we just kind of need to go from there. So firms A, B, or C can be chosen, right? So it means out of these three, we have to assign two to them. This turns out to be very similar to the supermarket question. All right, so we know we can go to firms A, B, and C. And I'm going to say A, B, or C, all right, because we can go to any of those three. We know that Y sub 1 denotes the number of contracts assigned to firm A, and Y2 the number of contracts assigned to firm B, right? So if I do my little sample space here for part A, I'm going to go to the next page and do this from there, all right? If I remember Y sub 1 equals number to firm A, specifically contracts to firm A, and Y2 represents the number of contracts to firm B. And then we also know that Y1 can take on a value 0, 1, or 2, so this is 0 less than or equal to Y1 less than or equal to 2. Make that look like it's supposed to, less than or equal to 2. And the same thing goes for Y2, because firm B could get both contracts as well if they wanted to, or they could get none of them. So that's kind of our range for our random variables. So if we think about, we've got either firm A, B, or C, right? So we can, or C, we got those three. Then little s is going to equal just either A, both firms get A, or A gets both contracts. This is representative of the same thing as like an ordered pair, but I'm just going to write them as AA. A could get one contract, B could get the other. All right, because there's three firms, and each one of them has a chance to get. Each contract could go to any of the three firms, so there's three choices for each one. So it's the same thing as the supermarket question. We get 3 squared, which equals 9 outcomes. That's how I figured that out. It's the multiplication principle. It's like contract 1 has 3 places it could possibly go to, and firm 2 has 3 places it could possibly go to. So back to the S part here. So I know contract 1 and 2 could both go to A, 1 could go to A, 1 could go to B, 1 could go to A, 1 could go to firm C, right? Just kind of following a very similar thing that I did in the supermarket example. I kind of continue on. I go, okay, well now 1 could go to B and 1 could go to A, 1 could go to B, both could go to B, and then 1 could go to B, 1 go to C. Finally, we got C, 1 to A, C, 1 to B, and C and C. All right, so this is very, very similar. So if we think about our y1, y2's values, possible values, they can be 0, 1, or 2 depending on which firm they went to. And remember, y1, the random variable y1 represents the number that went to firm A. So this very first here, this very first ordered set for AA means both of them went to A, so you get a 2, 0. It's looking familiar so far. AB, 1 went to firm A, 1 went to firm B, so we got 1, 1. Here we got 1 went to firm A, so y1 gets a 1. None of them went to firm B, so 0. Looking here at BA, 1 went to firm A and 1 went to firm B. BB means they both went to firm B and no contract went to firm A, so 0, 2. BC is going to be, I think you're following along with me at this point, means that we get 0, 1. We got 1 to firm B but none to firm A. We got 1 to firm A, none to firm B, none to firm A, 1 to firm B, and then CC, the last one here, is going to represent none to firm C. I mean none to firm A or B, so 0, 0. So there we go. There's our set of y1, y2, and we can answer part A rather easily by doing the similar thing that we did with that supermarket question. 0, 1, 2 for y1, y2 is 0, 1, or 2, and it looks like we have 9 outcomes possible in the set, right? The original set. So each one of those has a probability of 1/9 of occurring. So we just need to count them up again like we did with the supermarket question, and I think they're going to be pretty much the same. So 0, 0 only happens once, so we'll call that 1 over 9. 1, 0, y sub 1 equals 1, y sub 2 equals 0. So 1, 0 is the ordered pair I'm looking for. I got 1, 2 of those, so 2/9. Yeah, this is going to be exactly the same. 2, 0, y1 equals 2, y2 equals 0. That happens 1 time. So it's 1/9. Then we're looking for 0, 1s. 1, 2, 2/9. 1, 1. We got 2 of those. Be 2/9. This is going to be 0 because there's no 2, 1. y1 equals 2, y2 equals 1s. Ordered pair up there. Matter of fact, this is going to be 0. This is going to be 0 because the last one is 0, 2. And if we go by the table, the 0 column, the 2 row, that would be, this is 1/9. And we're done there. Part B asked us to find capital F of 1, 0, or the distribution function of at 1, 0, with 1, 0 in place. So we're going to do F of 1, 0, which is again the probability that y1 is less than or equal to 1, and the random variable y sub 2 is less than or equal to 0. We can definitely find this. Remember, this is taking on the values 0 and 1, and this one just takes on the value of 0 because we don't have anything smaller than 0. So we're just making the ordered pairs P of 0, 0 plus the P of 1, 0, and that's all we need there, and that was 1/9 plus 2/9 equals 3/9 or 1/3. Okay, so that's pretty much the first problem. Let's move on to the next one, problem 2. It's got a little bit more we got to think about here. It's a little bit different. It's similar to a problem though that we did back in the very first one of the very first sections in chapter 3. It's just taking it to another level. So we have 3 balanced coins are being tossed. All right, so kind of like the underline the things that matter. So we got 3 balanced coins being tossed independently. So they're independent, which means we can use multiplication rule. One of the variables of interest is y1. So y1 represents the number of heads, and y2 denotes the amount of money won on a side bet. All right. So the side bet, the betting goes on in the following form. It said if the first head occurs on the first toss, so if you flip all 3 and you get a head on the first toss, you win $1. So you may not want to get a head on the first toss based on the way they're set up. They're this here. If the first head occurs on the toss 2 or toss 3, you win $2 or $3 respectively, right? So if your first head appears on toss 2, you win $2. If it appears on toss 3, you win $3. So you really would love it not to appear to the third toss, right? And then if no head appears, you lose $1. All right, so the range for y2 goes from -$1 up to $3. All right. The number of heads we have to think about when we flip the coin 3 times. The maximum amount of heads you could get it would be 3, right? If you got all 3 of them as heads, or you could get none of them to be heads. So y2 is going to range from 0 to 3. If we think about that. So they want us to find the joint probability function here, and then also asks us what is the probability that fewer than 3 heads will occur and you will win $1 or less. That is find f of 2, 1. Okay. All right, so let's do that on the next slide so I've got more room. So we know we did 3 coins being tossed, so we got to think about the regular sample space here. And the number of outcomes, each coin has 2 sides, right? So those 2 sides, we're flipping 3 coins, 2 cubed here in this case. We got 2 objects, or 3, we got 2 possible outcomes for each object. We're raising to the number of coins we have, and that tells us that we have 8 possible outcomes. We know that y1 equals the number of heads, and since we're flipping a coin 3 different times, then little y1 can take on the values as big as 3, but no smaller than 0. The random variable y2 is defined as the number of money money won or lost, if you think about the -1. And those values there for y2s can be as small as -1 and as large as $3, right? Because we get a head on the third toss, that's $3. So to keep all this stuff in our minds. So I'm going to come with an outcomes list, kind of like we did with the ordered pairs stuff, except for I'm going to have ordered triples here. And I'm going to think about when I flip a coin 3 times, there's 8 different outcomes. We could do this as we could have all 3 of them be heads, right? We could have a heads, tails. We could have a heads, tails, heads. We could have a tails, heads. And I'm just looking at that as like I started with 3 heads, and then I went with 2 heads, and I moved the single tail around. Now I'm going to have a single head with 2 tails, and I'm moving the head back and forth. And so the next one would be tails, heads, tails. Then tails, heads. And that's 7, I do believe. 1, 2, 3, 4, 5, 6, 7. I'm only missing the one with all tails, and so the last one would be triple tails for all 3 coin tosses. Right. So now we have to think about what y1, y2, what possible ordered pairs am I going to get here, so I can help build my table a little bit easier. All right. So if I think about the first one, right, y1 is the number of heads that appear. Well, we've got 3 heads here, so this has to be 3. All right. And then y2 was the fact that y2 is the fact that you have how much money you've won. So if you remember, the rules stated that if we tossed a head on the first toss, we won $1. So in this case, our y2 value would be 1 to represent the $1 we earned. All right. Matter of fact, that's going to be the case for anywhere where there's an H as the first entry. As a matter of fact, this next one, a head was tossed on the first one, but there were only 2 heads in the group. The next one, there were 2 heads in the group as well, but we still earned only $1. Actually, in this case, our head came on the first one again, so we got $1, right? This fourth choice here is tails, heads, heads. We do have 2 heads, but the first head got flipped on the second toss, which means we earned $2. All right. The third one said that we got a head on the first again, and there's only 1 head this time, so there's only 1 head, but it was on the very first toss, so we only won $1, so that's 1-1 according to the random variable definitions. We have tails, heads, tails, so we still only have 1 head here, but it appeared on the second toss, so we win $2. The only time we can win $3 is this tails, tails, heads. There's still 1 head there, but we got it on the third toss, so we win $3. And then lastly, we got no heads here, so we get a 0 for the heads and a -1 for the tails. I mean, a -1 for the amount of money we lost because we didn't flip a head at all. All right, so no heads that appeared. So recall that these are 8 outcomes, so all outcomes here have probability of 1/8, right? But our probability distribution may not be exactly that, especially if we have matching pairs up there. So again, we're going to create our table, y1. Y1 can take on the values 0, 1, 2, or 3. All right. And then y2 can take on 4 values as well, -$1, $1, $2, or $3, and that's y2. All right, so we got these guys going down here. So we go through and we find to see if there's anything there. So we do have a 0, -1. It only occurs once, so this is going to get a 1/8. We don't have a 1, -1 anywhere, right? So that gets a 0. We don't have an ordered pair 2, -1 anywhere, right? So that gets a 0. And we don't have a 3, -1, so that gets a 0. Do we have a 0, 1? We do not, so that gets a 0. Do we have a 1, 1? We sure do, it's right there. So that gets a 1/8. Do we have a 2, 1? We actually have 2 of those. And just for keeping in the realm of eighths, so we're going to write that as 2/8, even though that's a quarter. Okay. You're most likely going to get 2 heads in this. The most probable thing in this group is going to be that you get 2 heads and win $1. But it doesn't mean it's any more likely than all the rest of the stuff either. Do we have a 3, 1? We do. We have this one right here is the 3, 1, and that's going to be 1/8. Do we have a 0, 2? We do not. Matter of fact, we don't have a 0, 3 either, so go ahead and put a 0 there. We do have a 1, 2 right there, so that gets 1/8. We have a 2, 2 right there, so that gets a 1/8. We don't have a 3, 2 up there in ordered pairs. 0. We do have a 1, 3 though. That's the last probability we have, or the last event we have up there that's in our list. So that's going to be 1/8, and then everybody else will get a 0. So there you go. There's your list, and it said for part B, it said find f of 2, 1. So recall that's from the definition, that's the probability that the random variable y1 is less than or equal to 2 and y2 is less than or equal to 1. So again, this one can take on the values, y1 can take on the values 0, 1, or 2, and y2 can take on the values of -1 and 1. Okay. So we're looking at the probability of 0, -1, plus the probability of 0, 1, plus the probability of 1, -1, plus the probability of 1, 1. Notice again, I'm just taking that and pairing it with the y2 values, possible values, and then I just did the 1s and paired them with the 2, plus now I'm doing the 2s. P of 2, -1, plus P of 2, 1. Alright, and now I just have to go through the list up there and see what all those probabilities are. So 0, -1 was a 1 out of 8, plus 0, 1 was 0. It's basically that first column, isn't it? Or part of that first column. And then P of 1, -1. 1, -1 is 0. 1, 1 is 1/8. 2, -1 is 0. And 2, 1 is probability of 2/8. So it's 2, 3, 4/8, or just 1/2. All right. And again, if you didn't want to write all that out, it's just really simply it says y1 is less than or equal to 2. So anything less than or equal to 2, and anything greater than or equal to, or less than or equal to y1. So less than or equal to 2, less than or equal to y1 is that little box right there. Is basically what we summarized or summated for our answer. Okay, so you can use the table that way too. I don't care about that. All right. So last but not least is the toughest one. Okay. We've got 9 executives in a business firm, 4 of which are married. 3 have never married, and 2 are divorced. Right? So there's some things we need to keep in mind. So we'll write those on the next slide over here in just a minute, but let's read the rest of the question. 3 of the executives are to be selected. So we're choosing 3. Notice I said the word choose here. We're choosing 3 of the executives to be selected for promotion out of those 9 individuals. Okay. We're going to let Y1 denote the number of married executives that are in the sample, or the number of married examples that are chosen for promotion, and Y2 denote the number of never married executives, all right, to be promoted. So apparently we don't really care about the 2 divorced guys. But assuming that the 2 divorced people, we don't know if these are men or women, assuming that the 3 are randomly selected from the 9 available, find the joint probability function of y1 and y sub 1, y sub 2. So this is the one I told you is a little bit more difficult to figure out, and I kind of gave you a hint. This is kind of an extension on the hypergeometric sequence. So let's write down what we do know. We know we've got 9 executives total, right? And that 4 are married. I'm just going to call it Mar. 3 were never married. And 2 were divorced. All right. We know that the random variable y1 is representing the number of married that get promoted. And y2 represents the number of married not never married, right? Yeah, never. I was going to say number of never promoted. All right. Well, what values can y1 take? Well, there are 4 married individuals, right? So quite literally, y1 has to be somewhere between 0 and probably 3. So y1's really between 0 and 3. Can't be more than 3. Can't be less than 0. Same thing with y2, because we have 3 individuals there, so it's possible that we pick all 3 executives that have never been married to be promoted. All right, so that's a possibility as well, so we have that. But this being hypergeometric, we got to take a few other things into account. In other words, we need a formula to figure out the probabilities here. All right, so we got to extend the concept of the hypergeometric to, remember when we did hypergeometric, it was only really talking about concern with 2 events, or two chooses in the numerator, if you recall. And then there was the choose out of the total to get the total denominator value. Here we've got 3 different types of individuals, so we have to consider that we could choose any one of those, any combination of those 3 types of people to be chosen for promotion. I mean, we could choose 1 married person, 1 never married person, and 1 divorced person. We could choose all 3 married people, and none of the never married or none of the divorced. Or we could pick both of the divorced and only 1 of the married. You know, there's a whole bunch of different combinations here. So to help us solve that, what we're going to define the probability distribution function to be here is probability that y1, let me give myself a little more room here. P of y1 comma y2 is going to be defined as follows. All right, this, you would not have probably come up with this on your own immediately, but if you did, great. That's the probability that y1 equals y1 comma y2 equals y2. We're not doing a range here. We're just talking about straight up the probability distribution function. All right. The probability distribution function, not the PDF, not the CDF. We want individual probabilities. And this is going to equal the following. 4 choose y1 times 3 of the never married people choose y2 of them. All right. And then out of the divorced people, we've got a total of 3. This was my part of my hint. There was a total of 3 people we're choosing, minus whatever we chose for y1, minus whatever we chose for y2, and all of that has to be divided by 9 choose 3. All right, that is the formula that would get us our individual probabilities. If you get something funky in this last one, that means the probability is going to be 0. It's going to be non-existent. All right. So if you get a number that's either negative, you can't do something choose a negative value. You can't do a value choose a value bigger than itself. Those are not defined. So those will get a probability of 0 instantly. Okay. So we can probably kind of figure that out as we go here and save ourselves some time of what we have to calculate. So let's write our table out, and then we'll pull a calculator up there to try to help us out with the how we do this. So we got 0, 1, 2, 3 for the y1 for the married folks, possible choosing of the married folks, and then y2, 0, 1, 2, 3. All right. All right. So I got my table ready to fill out. So basically, we can figure out the denominator for any one of these guys. But let's think about what happens here. Let's pull out the old handy dandy calculator for a minute. And I'm just going to start plugging and chugging away here. So let me move this over a little bit so we can see the calculator without having to mess the screen up too much. There we go. So what do I have going on here? Simply is just plug and chug at this point. If y1 equals 0, y2 equals 0. Let's first of all just go ahead and figure out what 9 choose 3 is, so we don't have to worry about it in the calculator anymore. So I do 9 math, go over to prob, option 3, choose 3. I think it's going to be 84, if I'm not mistaken. It is 84. All right, so that's going to be the denominator for all any of these probabilities that are valid. All right, so I'm going to put in my calculator. I'm going to make myself a probability function here. 3, and this is going to be 4 choose 0, right? And then we can just call this back every time we want to use it. Math, probability. I'm going to just do a few of these. I'm not going to bore you to death, but I'll just give you the final answer in a minute. Choose, so this will be 3, the married folks choose 0, if we're doing 0, 0 for y1 and y2, respectively. And this last one is going to be 2. Math, 3, choose. Now, if we plug 0 and 0 into the formula over here, right, then we just end up 2 choose 3. But what do you think the calculator is going to do if I plug 2 choose 3 in there? Let me get this set up right. All right, cool. So if we do that, it gives me 0. So we know the probability of this particular and 0 when y1 equals 0, y2 equals 0 is 0. Right? So when we get something funny with that last one, it's going to go away. Or if we get an error, we can also assume the probability is 0. If you get if you try to do 2 choose a negative value, you'll also get a 0 in by your calculator as well. All right, so it needs to be valid across the board. So 0, 0 gives us that. What about 1, 0? If we put 1 in for y1, I'm going to call that back up again by hitting second enter. If we do 4 choose 1, 3 choose 0, so there's y2 equals 0, then my last value here is not going to be a 3 any longer, it should be a 2. Because remember, these second half of these choices should add to the total number of items or people or things you're trying to pull from the data, or that you're trying to make a list of or combine together, or the total number of people you're choosing to get promoted in this case. So that should give me a value of 4. And I'm not going to simplify these, and I'm fine if you on a thing if you don't simplify these. I like them all to be the same. They're easier to add that way if you have to add things up. So that's 4 out of 84. Let's do 1 or 2 more here. So what if y1 equals 2? Well, if y1 equals 2, put a 2 there, 4 choose 2. We're still not choosing anybody. We're going across the first row. We're not choosing anybody for y2, so there's no never married dudes or ladies or whoever's. But from the divorced people, we have to choose 1. And we hit enter. And that should give us an answer of 12 over 84. All right. And if I do 3, 0, we're going to go through the rigmarole. But 3, 0 is going to just say, really, it's just 4 choose 3. This will be 0, right? Because 3 minus 3 minus 3 minus 0 is 0. And all 3 folks came from here. We get 4 out of 84 again. So you can kind of keep going through this. I'm going to give you the rest of the answers now instead of boring you with me going through it. But if you keep following the same pattern, you'll start next at y1 equals 0, y2 equals 1. So now it'll be your last values in this little setup would be 0, 1, 2. You should get 3 out of 84. oddly enough. And then across the row there, you'll get 24 out of 84, 18 over 84, and you're going to get a 0 here because you can't have 3 people from group 1 and then 1 from group 2. You've already added to 4. You've got more people than you were wanting to choose in the total. Yeah, you can't have that. So that's where you're going to get your zeros at. So you're going to get zeros here. 3 plus 2 is 5. That's way bigger. 2 plus 2 is 4. That's way bigger. 2 plus 3 is bigger. That's 5. 3 plus 3 is 6. So that gives you that away. 2 plus 3 is 5 again. 1 plus 3 is 4. So that little diagonal down in the bottom corner there are all zeros. But the rest of these have valid probabilities. So 0 and 2 you could do. And that's 6 out of 84. 1, y1 equals 1, y2 equals 2 is 12 over 84, and then this is 1 over 84. 0, and you chose all 3 to be the never married people. So there's your probability distribution. It's a little bit much here, but that is all there is to this one. And the key component to be able to figure that out was knowing all the information we had at our disposal, but specifically knowing this right here was important. Okay, and that wasn't something that maybe has stuck out to you, and that's okay. That's what we're here to learn. We will learn what this is called. It's called the multinomial. It's not called the multinomial probability distribution. It's just the hypergeometric distribution just extended out to a third argument, so to speak, in the numerator. We have had things kind of like that when we just did probability in chapter 2. Kind of taught you that you could do this as well. This is just a formulaic way to think about the hypergeometric distribution with more than two groups you're choosing from. All right, or subgroups, I guess we should call them. Anyway, hope this was helpful. If you got any other questions about it, please ask me. We'll start on double integrals next week, so expect my lectures to be a lot longer next week. Anywho, you guys take care, and we'll talk to you later. Bye.